Okay, so the thin lens equation and the magnification calculation, again, as I stated moments ago, these equations are exactly the same as what we've seen. It's just in the location of images versus objects. Again, we've already seen it. With mirrors, we expect light to reflect. The real world for a mirror is in front of the mirror, back where the light came from. In terms of lenses, we expect light to go through. They're transparent materials. So the real world for lenses is on the opposite side of where the object is. But other than that, the mathematics are identical. I'm going to get you to draw something here. Don't draw that. I'm going to draw it on the board so you can follow along on what I'm drawing. This is really kind of overwhelming. It contains all the information we need, but because I'm recording, I'm going to leave that picture up as I draw it on the board so you can follow me the way I want you to draw this particular thing. And, yep. Rulers, yep, I'll get the rulers out. Now, this picture is nothing special. It is simply, what's that? No, you don't need a protractor for this. I am simply going to draw a ray diagram, all right? And on that ray diagram, I'm going to label where all the important distances are. Because just like the mirror equation, I need a distance to the object, a DO. I need a distance to the image, a DI. I need a height of the object, an HO, a height of the image, HI, and I need DX. So that's what this picture is. And so I'm just going to put it on the board again for the video. It's there. So I'm going to simply draw a principal axis, simply a straight line through there, all right? And we can label that PA. And I need to draw a lens of some sort, and I'm going to draw a converging lens. So right in the middle of my line, I'm going to eye it up, a perpendicular line with the arrows pointing up and down to represent the fact that this is a converging lens, fat in the middle, thin on the edges. And then I'm going to choose a focal length. And again, for you guys, we've been doing something like 2.5 centimeters. That seems to be working well for our paper, so you can go ahead and do that now. For the board, I'm going to pick 20 centimeters. No, we'll go with 15. This is a terrible meter stick I've got in my hands. I'll go with 15. 15's not so bad. That means if I put this on 30, I can do the 2F, and I can do the F, and there's 30, there's 45, and there's 60. So again, I've got the PF, and the SF, and the 2F, and the 2F. All right? And just to sake for my example here, let's draw our object beyond the 2F, not too far, and how tall you make it, it doesn't matter because I'm simply doing definitions of things. Okay? So we know our equation already is going to be 1 over F is equal to 1 over di plus 1 over dou, right? It's the same equation. So all I'm doing now is defining where those things come from. So to start with, even before I draw my ray diagram, the distance from the lens out to the SF or to the PF, it doesn't matter, is our little f. That represents the focal length, if you recall. Okay? And my distance out to the object here, because I've already put that down, I'll put an O on the top of that, object. My distance from the lens out to the object is my DO. I just put arrows on there to talk about that DO. All right? The height of this object is HO. And now let's find the image. I'm going to find the image using regular ray diagrams, but we're going to get away from the ray diagrams in a minute. We're going to use the equations. So to just complete my definition, I'm going to put a ray that comes in parallel to the principal axis. I'm going to put that ray through the principal focus. And I'm going to keep it simple here. I'm going to use the vertex rule here, rule number 3, just like they did. I'm going to put a ray through the vertex, through the middle. And my fat chalk doesn't do a very good job because it's hard to get it right in the middle. And as we know from the previous lesson, where those two cross, that produces my image. And that distance out there, DI, from the lens out to the image is DI, all right? And I've got here HI, all right? Okay? Now, on my next slide, I've defined all those things, but we've already defined these. We've defined them in terms of the mirror. I guess I'm going to have this being written down as maybe optional, all right? Like you can write this down if you want, but we've seen this in terms of the mirror. Let me maybe point out the differences, all right? Again, if F is positive, by the way, that's a plus with a VE. That's my short form way of writing positive. If F is positive, what type of lens do you think it is? We had this when we were doing the mirrors as well. I could have a negative F, or I could have a positive F. If F is positive, what do you think? Anybody remember from the mirrors? There's a correspondence to the mirrors that goes with this. Yep. It's converging. It means that the rays are coming together. So if F is positive, it's converging. All right? If F is negative, it's diverging. Okay? Some other important things that go with this. If DI is positive, okay? And in actual fact, I can put that on my picture over here. This is positive DI land. I don't know how to write that. DI positive. If you have it over here, DI is negative. And that goes with, expecting the light to go through. In a lens, we expect the light to go through. That's what it should do. So the DI is positive if it's on the other side. What type of image is it if it's positive? If DI is positive, and we start with our object here and the light goes through, what type of image is it? It's real. So if DI is positive, that actually determines whether it's real or not. If DI is negative, it is virtual. All right? For DO, the real side is on this side. Can you have a virtual object? If you put more than one lens together, you actually can have a virtual object. You can take a virtual image from lens 1, and you can put a second lens in front of that, and it will magnify the virtual image. You can actually have an image from lens 1 that is virtual be an object for a second lens. So mathematically, you can have a virtual object. It's a little weird, and I'm not going to put it together, but we're going to be doing biology next. It's causing me a little stress because I don't know biology very well. I'm already looking ahead at the notes, and I'm feeling a little stressed. But a microscope is made up of multiple lenses. It's called a compound microscope because it has more than one lens. And the first lens that does the magnifying makes a virtual image, and then the second lens makes that virtual image even bigger. So for the second lens, the object is virtual. It's kind of neat. to do ray diagrams with these two lenses back to back can be quite complicated. We're not going to make you do it, but it can. Yes?
For a diverging or a converging,
Yep.
for converging, the left-hand side is the virtual world. But
Yep.
when it switches for diverging,
It's still the same.
so the left-hand side becomes the positive.
No, no, it's still the same. If
EI is negative.
No, for diverging, we're going to end up with negative, and it's still going to be on this side. We're going to end up with it back on this side. That's still in the virtual world of a lens. The front of a lens is virtual. If an image is in front of a lens, it's virtual. And for a diverging, if I end up with a virtual image over here, it will have a negative DI mathematically. That's how you're going to know.
But isn't the PF on the left side?
It is, but we're talking about the value for F, right? The PF is on the right-hand side, so it is positive. For a diverging, the PF is on the left-hand side, so that's the negative value of it.
Oh, okay.
Yep.
All right.
Yep. With the PF on this side, it makes the value of F negative, and there we have it right there. Okay? All right? Another thing. Remember, actually, I'll put the equation down in a moment. I told you to take a look on the last day when we were looking for some trends in these particular pictures. If magnification is negative, what does that tell us about the image? If the magnification is negative, it's inverted. And if the magnification is positive, it's upright. I heard somebody whisper it. Upright. But there's also another link that goes with it. All of our upright images, what type have they been? If they're upright, they have a particular type every time. I'm not talking diverging, converging. I'm talking about image type, that last thing that we do with the salt. Yep. They're always virtual. All right? When you have that negative DI, you put in the equation, it makes a positive magnification. One other thing. Magnification is greater than 1. What if the magnification is greater than 1, like 1.2 or 2.5 or 15? What does that do to what does it tell us about the size? It's greater than 1. Yep.
The image is bigger.
It's bigger. Bigger. If magnification, I got to be careful with this, is greater than 0, I got to be careful how I write this down. Greater than 0, it's in between 0 and 1. That's a tough thing to write. Magnification is, I'll just write it down, between 0 and 1. In other words, it's a decimal value. What is it? Smaller. It is smaller. And what's our other option? If it's 0, that's not a magnification. It just wouldn't be there. You'd have nothing. So it can't be 0. It can never be 0. Negative, we've taken care of the negative. I've got bigger than 1. I've got between 0 and 1. Yep. If it's 1, it's the same. If m is equal to 1, it's the same. So that covers pretty well all of our possibilities. Okay? Let's do some examples. Before we do examples, let's write down again our equations here. Don't worry, you can write down the thin lens equation. I've already talked about all this stuff, so you don't need to write down the bullets. I usually put 1 over f first. 1 over f is equal to 1 over di plus 1 over dou. So again, you write that as the thin lens equation. No need to write all these signs because I just wrote them down for you. Yep, everything's exactly the same. It's the same set of equations. The only difference is where the positive side and the negative side. On a mirror, the positive side is back that way. Negative side is back and behind, but that's the only thing, those flips. Okay, yeah, don't worry about that. Magnification equation, high over ho equals negative di over do. So whether you're dealing with a lens or a mirror, your equations are the same. All right, beautiful. Yep, we've already got this written down. Good stuff. That's good. Positive for an upright, negative for inverted. Magnification has no units. We've got all that good stuff. All right, now just some examples. So these questions are fairly similar. Find DI, find M, find HI, describe the image. Since we did the mirror equation? There you go. I don't even remember how long ago it was. So again, calculators, inverse key. If you got the hang of this stuff, it's really straightforward, and I'm hoping it is at this point. I know some teachers get all excited about write all your information down. Make sure you write an information table. Well, if we're talking about some pretty simple numbers that we're pulling out of a statement there, I don't need to see an information table. If you're not sure about where things are coming from, then write an information table. But I've got here 1 over f equals 1 over, oops, that's not a 1. 1 over di plus 1 over do. What am I putting in here? 1 over, what's the f? 17, it's converging, so it's positive, equals, I always write 1 over di plus 1 over do, but I usually put the object first. 1 over, what's my object distance? 48 centimeters. 48 centimeters plus 1 over di. Now I'm hoping our ability in our inverse key pressing allows us to almost jump right to the end. What's the inverse key? Excellent. What does the inverse key look like? What does the inverse key look like? Yep. X to the negative 1. What else could it be? 1 over x. 1 over x. We might need one more step here. Remember, we've got to bring this to the other side. 1 over 17, bringing the 48 to the other side, minus 1 over 48 equals 1 over di. 17 inverse minus 48 inverse equals. That's not the answer yet. Inverse the answer again. Flip it back. Shane, what do you got? 26.3. That brings us back to our good old significant digit debate. 2 significant digits all the way through. This should be 26, but don't sweat about it. Let's not get too excited about significant digits. We got all excited last time. Centimeters. That's 2 significant digits. That means I measured it with a meter stick that has exact centimeters, and that candle was exactly right at the 5. So it wasn't like 5.1 or 4.8. It was exactly 5. So I can express to you how exact the 5 is. And that's what significance do. They express the exactness of a measurement. But again, I didn't want to debate it, but no. Emily wants to bring up a significant digit debate, but that's okay. It's a good debate. All right, what else do I want? I want to find M, would be the next step. M is equal to negative di over dou. Negative, what's my di? 26.3, the do, 48. And what do we get? Have you done that yet? As we debated significant digits? Negative 0.54. Okay? We don't like it? We're getting multiple yeses and nos. 5.5, we're rounding to 5.5. Not a big difference, not a big deal. 5.5, we like it better? So what's the HI? Once you have the magnification, it's pretty easy. Take that magnification and multiply it by the size. Yes? 7.4. We're now questioning our rounding. 7.4. 2.7 is fine. That's two significant digits. That's good. What unit would HI have? Centimeters, just like all the rest. Centimeters. What you're doing is you're taking the height of the object. What is the height? 5 centimeters. And you're multiplying it by this magnification factor, negative 0.55. Pardon for running off the edge there. That gets you negative 2.7 centimeters. Size. What's the size of this thing? Smaller. How'd you get that? Yeah, that's a good way of doing it. The magnification is between 0 and 1. And the height is less than the other one. Smaller. Attitude. Yep. Inverted. And how'd you do that? What'd you look at? The negative on the magnification. I like it. Location. We can be very specific here. When we're doing the SALT and we're doing it with an equation, you can tell me the exact distance. Where is this image located? (26.3 centimeters). 26.3 centimeters from the lens. Do we need to say on the opposite side of the object? Not really. I guess if we had a virtual image, we would want to specify that it's on the same side as the object. So I'll just go with from lens. I have no problem with that. And what type is this? What type of image would this be? Yep. Real, and how did you get that? Sorry? The magnification is negative, and if it's inverted, it seems to always be real. Yep. What else could you use here? Yep. The DI is positive, and that's the real world. Correct. Okay? Let's do another one. That's fun. Now this one says a diverging lens has a focal length of 29 centimeters. On the little practice problems that I have you do, I've put the negative in there for you. In the past, when we used to have this with the grade 12s, we wouldn't put that in, or grade 11s, we wouldn't put that in. We'd expect them to know to put that negative in for a diverging. You probably would have did it anyway. No? All right. Well, then you're welcome. Yep, question? That's correct. If we end up with our image on the left side, right, with a negative value would bring us in front of the lens, then yes, then it becomes virtual, you bet. That defines what it is. That negative, if we get a negative DI, That's going to define that for us. Again, I got to bring that to the other side. So if I'm solving these mirror or lens problems, that's the number of steps, right? That's good. So again, negative 29, or it's, for your calculator, it's likely 29 negative. It depends on what the calculator is. Negative 29. Inverse, minus 13 inverse, equals. And then you got to invert it one more time to get that answer back out of it. And we got a lot of negatives on the left. I think we're going to get a negative DI somewhere. And again, if you don't have a calculator, you need to borrow one in order to participate. And I think Wilson's our only non-participant today.
Well, I don't have a calculator.
What do we have for DI? Yep. Negative 9. Negative 9.0 it should be, but that's okay. Centimeters. We're not going to debate that. M is negative di over dou. Negative of negative 9 over, what was my object? 13. 13. The two negatives cancel away. 9 over 13. Where did the 9 come from? Do we not have a DI of 9? 8.97. 9.0 is great. Yep. 0.7? 0.7? Positive? 0.7? Yep, yeah, it's got to be. Yep. Again, HI, you can rearrange the equation. This is M equals HI over HO, right? So what I'm doing is I'm bringing the HO to the other side. HI is equal to HO, the height of the object, times whatever that magnification factor is, okay? So the object was what, 5 times 0.7. What do you get? Sorry? 3.5? 3.5 centimeters. Okay? And let's go through the salt. Size. Nobody wants to share, and Justin seems to tell me all the answers. Oh, okay, go ahead now. Is it bigger? No, I don't think so. What's my HI is 3.5. HO was 5. Smaller. Attitude. Upright, how do you know? Yes, M's positive. Upright. Location. Again, we can be specific. Yep. Yeah, but let's be a little more specific this time because of the negative. We'll say 9 centimeters in front of the lens. It's actually out in front of it. 9 centimeters in front of lens. And putting that in front tells us that it's, well, this particular type. What type is it? Yep. No, it's not real. Puts the hands up with all the confidence. No, not weird. Try again. Yeah, virtual. 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 Virtual, why? Because it's in front of the lens and the DI is negative, and I don't know what other evidence you need there, Megan, in order to get virtual out of that. Anyway, okay. So we've got some practice problems. There's some textbook work you can write down. There is a sheet on today's date, which is practice, all right? There is also an assignment, right? And I want you to do the practice first before you do the assignment. No, not due tomorrow. We'll give you a couple days for that. And I will show you online where these sheets are. And I was going to talk about uses of lenses, but we'll see. We'll see how the working goes. If everybody's working away, I got no problem with you using it. Let me show you what this stuff looks like. Now it says Lens Math Worksheet, but I changed the title. So go into the PowerPoint here. Let me get rid of this. So here we've got lenses. So the thin lens equation practice, I'd like you to do it first. There's only 4 of them. It looks just like what we just did. It doesn't actually ask you for the HI in here, I noticed, but do it anyway. Just like we did those, there's 4 of them. So please practice those. I've done the solutions and put them on the course content solutions page. When you're done that, give me a quick show that you're finished it, and then you can go ahead and you can work on this lens equation assignment, which looks just like the one we did for the mirrors. Let's bring that up here. And again, it talks about a converging lens, and it says find using a ray diagram. So remember, we did scale ray diagrams, right? Good times, right? I want a scale ray diagram, and then I want the calculations to support it. And again, it's 1, 2, 3, 4. Thank you for groaning. That means I'm doing my job. That's awesome. And this is going to be due in 2 days. All right? Yes, it does, being that today is Monday. Okay, go ahead. Hold on one second. Let me stop recording here before we entertain a million questions. You can work on the worksheets online and not worry about the homework necessarily. Let me just stop this recording world here for a moment.